So in neuromuscular junctions, some folks refer to this as a motor neuron. Or a motor unit. What we're looking at is the interaction between your muscle system, your nervous system, and your endocrine system. Your endocrine system deals with hormones and chemicals and the release of those. So we actually look at this neurotransmitter known as acetylcholine to be released and cause a muscle to contract. Now, its release will tell the muscle that it needs to contract, but the neurotransmitter, the acetylcholine itself, is not enough to make the muscle contract. What we actually need is calcium to come in and be released, and when that is released, that's when we see muscle contraction, and this is where we see our calcium ions coming in to initiate a muscle contraction. We need a lot of things working together here. This is not just a simple one-step process. And what we're looking for is this calcium to actually bind, and when it binds, that gives us, when the calcium binds to these sites, that's what's actually going to give us a space so we can actually contract our binding, or contract our muscle. So when we get calcium coming in, we're opening up spaces, and you see this diagram is a little hard to follow, but this tropomyosin is currently running along, and it's literally blocking these spaces. These things that look like olives, this is the actin that we talked about before. Those binding sites for calcium are blocked until we can get that tropomyosin out of the way. And tropomyosin is actually moved by calcium binding in these sites and shifting, essentially moving this rope out of the way, so that we then open up these spaces and we can bind more calcium. And by binding more calcium to the tropomyosin, you've opened up these spaces, and this is where our myosin heads are going to bind. So we're using calcium to get that tropomyosin out of the way so that we can open up the space for the actual myosin heads to bind. And the only reason this happens is because of motor units. The acetylcholine and calcium are required for these muscle contractions to occur, but what we look for as the initiation point is actually a single neuron sending a signal that says the muscle needs to contract. And so what we look for in you is this very close association between nerves and muscles. So if you have one nerve coming in to one muscle, you get very, very good control, or what we might refer to as fine motor skills. However, if you have one nerve coming into 100 muscle cells, you have less control. And that's okay. There are some areas where you don't need fine precision motor skills, right? But regardless of whether it's one nerve and one muscle or one nerve and 100 muscles, we still have acetylcholine involved and we still have calcium involved. And what we're actually trying to do is cause a twitch to occur in our muscle cells. And that twitch comes about, or that contraction comes about, based on this use of ATP. We have talked aerobic respiration before. You know aerobic requires oxygen. Fine. In the absence of that, in the absence of oxygen, the mitochondria don't get the oxygen they need to produce ATP, so we produce ATP very quickly through lactic acid fermentation. We talked about this in cell respiration. If you're not familiar, you can go back and check that out. but it was the use of oxygen to increase ATP production. If we don't have oxygen, we have decreased ATP production. We build ATP as fast as possible through anaerobic respiration. And that anaerobic respiration actually causes the buildup of lactic acid, which is what many of you know as muscle or runner's burn. The twitch is dependent on the type of muscle. In your body right now, you have what we call fast twitch and slow twitch fibers. Fast twitch are what I associate with white meat or the wings of chickens. It allows very, very fast contractions, lots of power, but short time period. Slow twitch fibers, the red meat or dark meat I have here of our chicken leg, these are slow, constant contractions. So you can also think about this like sprinters with a lot of fast twitch muscles versus marathon runners with a lot of slow twitch fibers, if you don't like my chicken example. So they actually looked at the production of ATP and the production of muscle contractions under different conditions. And so when we look at long distance runners, they're doing a lot of aerobic respiration. They've got a lot of time to get in oxygen to make ATP. But if you're sprinting, you're actually using a lot more of the stored ATP. And if you sprint slightly longer distances, quarter mile and half mile types of things, you're looking at the buildup of lactic acid fermentation. And so often you see this runner's burn. So they started to think about what does it actually mean to have these different muscle types. Well, it's based on myoglobin levels, so your ability to bring in oxygen, the number of mitochondria, and the number of capillaries that are associated with your muscles in particular. So all of this contributes to the amount of oxygen that you have available and then the number of ATP that you can actually produce. So they looked at it in different runners. So we've got sprinters, we've got endurance athletes, and then we got couch potatoes. So slow twitch and fast twitch, and then something in between. So you notice that the slow twitch fibers, remember we said that this was long time periods, slow, constant contractions. We see a lot of those in our endurance athletes and very few of them in our sprinters. Instead, in our sprinters, we see those fast twitch muscles, things that we need to be responding very, very quickly. So this is going to be based on stored ATP and in some cases, some fermentation reaction. Whereas our long distance runners with our slow twitch fibers are going to produce all their ATP through their oxygen and their mitochondria. So different numbers, different concentrations of these different types of fibers. So you can actually see there are muscular differences between sprinters, endurance athletes, and Dr. Connolly, who is your average couch potato. What about Botox? Why would I even talk about Botox now? Well, I talk about Botox because it actually blocks the nerve's ability to send acetylcholine, so there is no contraction. And actually what it's doing is paralyzing the muscles so that they can't release acetylcholine. If you can't release acetylcholine, you get no contraction. And why would we ever do this? Well, it turns out that Botox is now one of the best-selling drugs in the United States because people use it to get rid of forehead creases, frown lines, and so on. It was actually approved in 2002 as that use, and it is a toxin. It's a toxin produced by a bacteria known as botulinum. And some of you may know botulism, so actually associated with bacterial infections. We're using the toxins released by the bacteria to essentially paralyze your muscles. Now, as a cosmetic procedure, in 2007, there were about 2.7 million procedures. By 2012, we were up to about 6.1 million procedures. Now, I know that some of you are now using Botox for things like migraines. So we are looking at alternative options to this toxin, but these are all about cosmetic surgery.